Hi, everyone. Thanks for joining. As Abby said, we're really excited for everyone to be here, and we really are encouraging an interactive webinar. I know Ruoying has some direct questions for everyone, and as do I. Ruoying's going to start off by discussing the actual modeling activities, and Charlton and I are going to discuss product development. So just to give you a little bit of background, this project is funded through the US IUS, which is the Integrated Ocean Observing System Office. The goal is to take is to create better models for the nearshore environment, and the goal is to take National Water Center model products and tie those to ocean model products, such as Ruoying develops, to create better tools so that we can do a better job with navigation and safety and ecosystem response and ecosystem resilience. So that's just sort of a brief intro. This project began in 2019. And goes through 2022. So we're really at a point where we need to start working with the communities a lot more closely so we can get feedback from you so we can make sure we are developing models and products that really meet your needs. So Ruoying, I'll turn it over to you.
Wonderful. Thank you, Jennifer. Abby, do you have my slides?
I am going to promote you to presenter so you can share your screen.
Sure, let me do so. Show my screen. Give me 1 second. Screen number 2. So do you see my screen number 2?
Yes, we are seeing the
okay.
The beautiful camp photo.
Okay. So do you see the slide, the first slide?
Yes, I do.
Wonderful. Great. Well, thank you.
1 second, Dr. He. If you guys can't hear us, there should be an option to call in. Please use the phone call option. We have one attendee who's having trouble hearing us.
All right. So shall we start?
Go ahead and get started. Sorry about that.
Okay, no problem. Thank you. Good morning. Well, good afternoon, everyone. So my name is Dorton, as Abby and Jen mentioned. So I'm a professor at NC State Universities, and this project is funded by the county. So as Jen mentioned, so it's a 3-year project. We are 20 months into the process, and this is really a great partnership among universities and also SECOORA and also Fathom Science and Second Creek. And we just want to start by thanking NOAA IUS for supporting us to work on this very important and also very interesting project. So the goal here is to develop a integrated coastal water prediction ability that can deliver new water intelligence. And by doing so, we are able to support a variety of decision makings, both for the high impact weather events or for the routine water management, including the marine ecosystem health, transportations, and agriculture. So the idea here is to be able to accurately describe the interactions between the land and ocean. And in this case, we need to consider the coupling between the hydrologies and also the coast ocean at high resolutions and also high fidelity. So as part of this project, we're going to develop a prototype Bioclinic modeling system. So there's a suite of other applications using barotropic models focusing on the storm surge. In this case, we are focusing on the Bioclinic system. And by doing so, we are able to look into 3-dimensional ocean circulations, temperature, salinities, currents, and then to use temperature salinity to build a suite of other proxies to look into turbidities, stratifications, and eventually can also start looking into ecosystem health. And one of the key components here is to link with national water models output. So then the hydrology information is able to be transferred into the high resolution nearshore and the coastal ocean models. So we are going to look at 2 different river ocean systems, and we decide to use the Pamlico Sound in North Carolina as one end member, In this case, we're looking into a classic lagoonal system, and we have very energetic offshore circulations represented by the Gulf Stream, but also a very large lagoonal system with major river input. So this is one end members. The other case we are looking into is the St. John's River in Florida. In this case, this is more classic estuary system. And the idea is by looking into the two systems, we can generalize the lessons learned from building a prediction system for the two systems. So hopefully the idea and technology can be applied to other systems along the nation. And the project approach is to, as I mentioned, to develop a prototype river ocean prediction system by coupling the national water models. And this is run by NOAA National Water Center using World Hydro model. So National Water model is providing nowcast forecast at different time spans and frequencies. So there's a short-term, mid-range, and also long-range forecasting. And so then there's a real-time river information is coming from the NWM. And then we are using a regional scale Bioclinic ocean model to couple with the national water models to start looking into the ocean feedback to the fresh waters and see how the circulation is also by changing the sea level and temperature salinity also can feed back to the river models. And then by having this coupled system, we can look into a suite of state variables such as total waters, so including tides and surge, the currents, three-dimensional currents, three-dimensional temperatures, salinities, and also residence time, which can be a very important indice to look into stratification, for instance, for both sides. And by doing so, we are also collaborating with our NOAA colleagues at the co-ops and the National Water Centers and a Coastal Study Development Lab. And also working with you, many callers on the call, stakeholders, the end users, dealing with unique coastal ocean issues such as flooding, water quality management, ecosystem and navigation, so on and so forth. So the idea here is to use this larger scale model called Cnap. So this is the modeling system we have been developed over the years with the support from NOAA and SECOORA. So this is like the backbone circulation structures. So we're using the Cnap to provide the larger scale ocean circulation conditions. And then from here, we can downscale to two different study sites. So Cnap is a pseudo operational system that we've been running here at NC State for, I think, close to 4 years now. So it's delivering nowcast and forecast on the circulation condition. One of the unique features of Cnap is this is a fully coupled system. The ocean component is being simulated by the regional ocean modeling system ROMS. And there's also a regional scale WRF model, regional scale wave model SWAN. So when we run the Cnap, it's going to be a fully coupled system providing a concurrent model renditions for the atmosphere. In this case, for example, we're looking at the coupled WRF model predicting the sea level pressure, 10-meter wind, and we also have a coupled wave model predicted significant wave height and wave direction. And this is, for example, the coupled ocean model predicted the surface current, surface temperature, surface salinity. And so we had built a lot of experience on how to run the fully coupled models and how to run the modeling system in the operational sense. And for this, which provide lots of strong foundations for this COMT project. So for the COMT project, then we are using the Cnap ROMS model as a starting point. Okay, so then we are using the ROMS model as a L1, so-called the parent model, to provide the open boundary conditions for a two sets of high resolution sub-regional nested models. So in this case, we have a nested model for Pamlico Sound region and also a nested model for the St. Johns River region. So I'm going to show some results for each of the two regions, so we can see where we are and also get users' feedback. And I should mention, if you have any questions, please feel free to stop me. I know sometimes the talk can pretty technical, and if there's anything unclear, please let me know. Okay, so I'm going to show you some results. So this is the L1. I'm going to show you some results for the Pamlico Sound, and this is at higher resolution. Okay, so this is at 800-meter resolution. So intermediate L2 domain for the Pamlico Sound region. But to do the Pamlico Sound modeling correctly, we also need to pay very close attention to the surrounding circulations, in particularly the Gulf Stream. The Gulf Stream is only about 50 miles offshore of Cape Hatteras. So the strong currents, the bioclinicities, the temperature, salinity structures here are very crucial for us to be able to resolve the local dynamics. So in this case, we're looking at 15 days sea surface temperature. And at 800-meter resolution, you can start to see very rich structures. So you have a warm Gulf Stream moving offshore. You also have some cold freshwater, cold shelf water coming down from the mid-Atlantic bight. And certainly you have very interesting sound and ocean exchange. In this case, there's some cold water moving into the sound. And if you look at salinity, you can also see there's some fresh water coming out of the sound. Okay, so we've been spending lots of time to make sure this intermediate model, L2 model, is fully functional. And to do so, we have done a suite of model data validations. So in this case, we utilize extensive observations coming from satellite. For instance, this is AVHR satellite measure sea surface temperature. There's also a number of altimetry observations measure the sea surface height, as shown by the tracks, along track sea surface height measurement. And as part of IU's programs, there's very dense high frequency radar network. So all the brown dots here are the surface velocity measurements by the regional HF radar network. In addition, there's a buoy network maintained by NOAA and also by SECOORA and Marcus. There's also a Argo floats and a glider doing the surveys in the region. So all these observations are being utilized for the model validation of this regional scale model. We are in the process of collecting some inshore measurements inside the Pamlico Sound, for instance, and there's other model validation efforts is ongoing using the more nearshore observations. So I should mention that after my presentation, Jen and Charlton will be giving some demonstration focusing on the Pamlico Sound for this region, and also for the St. Johns River as well. So I should mention that one of the interesting process we are focusing for the St. John's, for the Pamlico Sound region, is hurricanes. So this is hurricanes and other high impact weather events. So this is one example, right? So it happened in 2008, Hurricane Florence. And this is from our L1 larger scale Cnap model. And because it is fully coupled, that gives us a very good opportunity to use this coupled model to look into the interactions among atmosphere, ocean, and wave. So this is sea level pressure produced by the wave model. So clearly you'll see the motions of the hurricanes when you track the low pressure centers. And then the hurricane is generating very strong upwelling, bring the cold water up to surface. So that's why you see a very clear cold wake. And this is corresponding wind fields, wave height fields, and the precipitation. Okay, so now we can zoom in. We can bring this large scale high impact weather to the local scale to see what's the impact of this event on our local hydrology, salinity, and nearshore circulation. So as we know, Hurricane Florence is a very powerful storm that dumped lots of fresh water. So precipitation, we're talking about up to 36 inches during the impact of Hurricane Florence. That caused major floodings. And this is the observations from Doppler radar. And this is a cumulative rainfall over 5 days, immediate after the storm. And tremendous runoff and floodings occurred as a result of Hurricane Florence impact. So one thing we've been working on, this is in collaboration with John Warner from USGS and also George here from Louisiana State, and George was a former postdoc of our team. So the idea is now we have this high resolution local scale model, so we can link hydrology, river hydrology with ocean and also with atmosphere. So what you are seeing here, the color shading here, this is surface salinity, and the back here are surface wind fields, okay? And then the color shading is over land. This is rivers. And in a few seconds, you will see a big blob of precipitation coming on shore. So this is where the Hurricane Florence is impacting. You have this larger scale precipitation event. And after this precipitation, you see there's an increasing in river runoff, and river will go further downstream into the ocean that causes the freshening of the salinity. Okay, so this particular case, we're building this system, couple system, to study Hurricane Florence, and the major river ocean impact happens at the Cape Fear River. So the impact in the Pamlico Sound is something that has not been our focus, but our next research step is to, look into the Pamlico Sound and then focus on the how the storm, not only the Florence, but other storms, is impacting the circulations, the salt budget, the temperature budget inside the Pamlico Sound. But the concept is the same, and the modeling system being developed for Hurricane Florence can certainly be also applied for other high impact weather events. So let me move on to a different site. This is in the St. Johns River region. So we are moving down to Florida. And I'm going to just show you the L2 model for the St. Johns River to begin with. In this case, we are looking at, again, some historical event happened in October 2016. And we are looking at this 800-meter resolution L2 model simulated sea surface height in color and surface velocity shown by the vectors. And in the middle panel here, this is model simulated sea surface temperature, and right panel here shows the model simulated surface salinity. Okay, so again, we have a very strong Gulf Stream passing by, and Gulf Stream is very powerful and also very nonlinear. So that's why you start to see lots of the frontal eddies, which promotes the cross-shelf exchange. So when we do the local scale circulation study, it's critical to get the boundaries, the shelf circulation conditions right. So this multi-level nested approach enables us to do so. So now we have a pretty good foundation for the L2 larger scale model. We can now study the L3. So all the information coming from the boundary is being provided by the L2 model. And this is two-way coupled. So what happens in the L3 can also feed back seamlessly to the L2 model. Okay, so at L3, now we are talking about a 160-meter resolution. We can really start to resolve all the detailed circulation features in the St. Johns River. And this is sea surface height, sea surface temperature, and sea surface salinity. So one of very interesting feature here, you see there's very dynamic exchange between the river and ocean. You see the fresh water, this river plume coming into the ocean, and then they can propagate southward along the shelf coastlines. And you also see the salt intrusion. So this is due to combined impact of the tides, wind forcing. In this case, October 2016, this is actually Hurricane Matthew. So when Hurricane Matthew coming closer to the St. Johns River, there's a very strong storm surge and also the influx of salty shelf waters into the river system. Okay, and as we have done for the Pamlico Sound region, we also look into a suite of model data validation. And this is very quickly showing the sea level the sea level comparison along different stations. And in this case, we're looking at observation and the comparison for 3 different models. So L1 larger scale, L2 shelf scale, and L3 river scale, and see how well they're able to compare with observed sea level. And we also look into comparisons of the salinities. So there's a number of in situ measurements conducted by the government agencies such as USGS, but also by the state of Florida. So they're collecting the time series that we are using for the model validation. So we have the modeling infrastructure in place. What we are working now in close collaborations with NOAA scientists, Moji in particular, is to refine this modeling system, calibrate model performance, so we can get a better and better model skill. I want to show you another case. This is Hurricane Irma, happened in 2017. This is again another larger scale storm that translated over the St. Johns River region. And in this case, we are looking at another feature we are able to bring into the modeling system, which is with wet and drying. So as a storm moving over the land of Florida, there's a major flooding, lots of precipitation, so you have a strong fresh water coming into the river system, and National Water Model is able to capture that increasing of fresh water runoff very, very accurately. And then we are bringing that National Water Model's output into this high resolution river models. And then when we turn on the wetting and drying, you can also see the impact of the storm surge, right? So that lots of wetlands and salt marsh, and they can be inundated. So you do see this this inundation, the storm surge conditions happening as the storm moving across the system. And you can also look into the temperature and also salinity features. So it really depends on the coastal management requirements. So if this is a storm surge or flooding, then the sea level can be quite useful. And if this is related to the water quality or hypoxia or water sanitation, then looking into the salinity can be quite useful. So Jen and Charlton will present the user interface our team has developed. So this is from the model, but there's different ways that when you use a web portal, you can sample the model fields in the different sections along different lines, for instance, to enable the users to do more interactive investigation of this modeling system. So in summary, so our team, we've been working really hard. So we're 20 months into our 3 years project. So we still have 60 months to go. So this is a crucial point for us to get the valuable feedback from our end user stakeholders. So to see what other needs or what other variables you are looking for. So what we have here is a prototype of high resolution models linking rivers hydrology with ocean. So this is a new coastal water prediction capabilities. We're hoping that that can be useful, supportive for our end users to make vital decisions on day-by-day basis. And we again thanks NOAA for their support, and this is a strong collaboration with the National Water Centers. So having their solutions from the National Water Models is crucial, and we're building technologies to link ocean with river in the two-way coupled cases. We are continuing refining the model skills by validations and verifications and the model refinements. And we're hoping that the resulting system can be valuable, can be useful for a suite of stakeholders activities, including floodings, coastal inundation, water resource, water supply management, water quality risk management, and also transportations and the navigation. So I think I will stop here, Abby, and then Jen and Charlton, if you are ready to do the demo of the web portal, I would unshare my screen and you can go ahead to share your screen.
Sure, and I will say real quick, if anyone has questions for Ruoying before we go on to the demo, feel free to chime in. Just unmute yourself and or type a question in the chat and Abby can read it out. And don't be shy.
Yeah, and to unmute yourself, you'll click the little microphone icon. I'm not seeing any questions in the chat though. And Jen, just to confirm, we are seeing your screen.
Oh, great. Okay, well, I will start moving forward a little bit here. And I'm going to apologize now. I should have locked my cat out, and she's sitting on top of my notes that I was reading a little bit off of, so hopefully I'll cover it all. But Charlton, jump in and save me when needed. So as Ruoying pointed out, Charlton and I are trying to develop products that can be useful for folks. Sorry, I see my cat in the video. Let me move her. And so we have really just created a wireframe at the moment. These are base level products to really get folks to start thinking about how they might want to receive data and information from the model output. And this is really just to get people thinking. This is not an end product by any means. This is a start. So I'm really encouraging folks, ask questions, jump in, don't be shy, you're not going to hurt our feelings if you don't like something. That is, we want to hear it. So give us the good, the bad, and the ugly. So to start with, if you want to see what we're doing or go along with me, you can see up in the address here, it's COMT, so comt.SECOORA.org. That'll take you to the exact page that I'm on. We do have a little bit of a range of visualizations. We started out over here on the right-hand side with draft visualizations, and we actually spoke to some folks with the St. John's Water Management District a couple months back, and they gave us some feedback on how they would like to interact with some of this data, other sites that they've used that gives good information for them. And so we took sort of this initial draft visualizations product, and we started working on the two you see, the middle, St. John's River, and the one on the left, Albemarle Pamlico Sound. So I'm going to start on Albemarle Pamlico Sound. This is more of our base level wireframe. And let me stop here. So when you come in, this sort of keeps your previous settings. So, you know, the last time we were in here, I was looking at a salinity level of 25 parts per thousand. And so when I came back in, it's taken me to that exact same place. So a lot of things you can do. You can just zoom out, use the map, and you can see the map of the Albemarle Pamlico, and you get the offshore environment. You can check on and off the different salinity levels. You can zoom back into areas that you're interested in. And then over on the right-hand side, obviously we're dealing with hindcast data. You know, we're not at the forecast stage right now. So what we've done is we just took a slice of data from June 3rd to June 13th and tried to plot what this might look like. So, you know, pretend it's June 2nd, 2016, and you want to see what the upcoming week looks like. This is what this may be. So we also went in and, well, there's two ways you could use this initially, and this is where we really are looking for feedback. You can circle around in this map, you can scroll into areas that you're really interested in, and you can kind of look and see, well, the forecasted salinity is not supposed to be over 25 parts per thousand. You know, basically once I'm past Oriental, and I can kind of move on up here towards Newbern, and I can maybe change this to 15, and I see that over the next few days, we may have salinity that's in the range of 15 parts per thousand, though, almost up to Newbern. So there's just sort of an investigative tool you can use this map for. But as you will notice here, we have selected and sort of predefined two locations. And if the folks in North Carolina that are on the phone, I know you're aware of the ModMon monitoring program that's operated by Hans Pearl. And so what we did is we took two of the ModMon stations and just Charlton made those, you know, put those on the map and said, hey, if I was a user and these are two locations I'm really interested in, I can pre-select locations. So that's what you see over here on the map. You'll see ModMon 7 and ModMon 9 in the map. depending if you're in here with me or how good my screen resolution is, you can see anything above 25 is slightly shaded a little darker than anything below 25. And I do have an interactive track line here, so I can see exactly that roughly around June 9th at 6 a.m., 4 a.m. rather, we're going to see salinity start climbing up above that 25 parts per thousand threshold. And it's going to stay that way until roughly June 11th, Saturday, June 11th. And then we'll see it starting to come back down before it pops back up again. Up at Station 9, we're staying pretty even keel the whole week. As you know, June's not typically a time when we see a lot of fluctuation in salinity, but it can happen. One of the goals that we have is to try to figure out what is a good tool to use. Do folks want that interactive map tool where they can really come in here and they can choose their own salinity ranges and drill into very specific areas? Or are these options, such as we're showing, where you can sort of predefine a few locations and then you can either come into the map and look at them, or we can create an email product where we just send you an email daily and you might get this map with a graphic and you can exactly see what's going to be happening. And it's just a PDF that comes to your inbox every day or every 3 days. However you want to set that up. Now, Charlton and I, when we were doing this, we just took a range of salinities and dropped them in here. So there's a lot of things we really want some input from you all on. Having sort of this predefined range, is this sufficient? If it is, are these the right units? Or do you want to be able to kind of use your own range? The other thing is we're only doing this, showing this with salinity at the moment. However, temperature and water level are all available, and we can and will provide products that are based on those parameters too. But it's just a starting point. We were trying to get some feedback, and we were just showing a base level of salinity data. Does anybody have any questions so far?
Yeah, we've had a few questions come in, Jen.
Okay.
One person asked if Dr. He could give a quick brief overview of Cnap, which maybe we could wait till the end of the presentation and you could go over that. And then we've had another person ask, dredging of the St. Johns River started a year or so ago and saltwater intrusion has been a concern. Has this been seen in the St. Johns models?
So I'm going to say that we do have St. Johns models, and we're going to show those just as soon as I finish up right here. And I think, Ruoying, I'm going to let you jump in on that because I know you've got bathymetry data. I don't know, though, if you have the newest bathymetry data incorporated into the model yet. I think you do. But do you want to answer it here, or do you want to wait till we move over to the St. Johns?
Why don't we move to the St. Johns? We can talk about St. Johns case together.
Okay. So, and just one note, we do have, when you see the St. Johns, this play button will make a lot more sense there. At the moment, it's just sort of an animation, and you can kind of see it just kind of moves you along both graphics at the same time. So you can stop it, but like we said, you also have the ability to look at any of the data along the graph line here. And this is hourly data, and this is surface data that we're showing. So this is hourly surface salinity data at this point on this map. So I'm going to go back and I'm going to jump to the St. Johns River. And as soon as you see the top graphic, everyone is probably going to, here we go. I'm going to hit pause. So now in the St. Johns River, we have a little bit more in our toolbox here that we're showing you. And you can see here we have 3D data available. And the surface level obviously is at the top of the map. And then as you go down the map, you're going down within the water column across this transect from A through E. Ruoying, you want to jump in on the question?
Yeah, so in this case, we're looking at, this is salinity. So this is along river channel salinity distribution. So when we study the salt intrusion, one of the approaches to look at along river channel transect. So I think this animation will probably need to reload this page, Jen. Because when you reload this page, yeah, okay, thank you. So you are able to see the day by day, in this case, I think it's hour by hour, evolutions of salinity along the river channel. So the station A, so that's a starting point of x-axis. So this is closer to the ocean. So essentially moving from A to E, we're moving upstream in the river channel. So that's why you see a pretty strong salinity gradient. And as you see that there's a pulse of high salinity water moving into the river channel, upper stream. And this is during the normal conditions, this is due to the tidal pumping, right? So when you have a strong wind, such as hurricane, and this has become additional forcing, so the hurricane pushing water further into the river, you will see more strong, significant intrusions of salinity moving from ocean into the river channel. So these particular models then become a pretty useful tool to show the extent of the salty waters moving into the river channel. So going back to the questions posed by the audience. So yes, so the salt intrusion questions can and will be addressed by these high resolution prediction models. The questions about dredging, yeah, so that's very important because we spend lots of time trying to get the best possible bathymetry data for this high resolution L3 models. And we are not claiming that we have exhausted all the data sources we have. So we spend lots of time digging into NOAA site, USGS site. But if any of you have more local bathymetry observations, please let us know, because we can use some local observations to keep refining the bathymetry. And this is our ongoing effort, trying to make some model better and more realistic, and by incorporating more and more local observations. So yes, if you have that information, please do let us know, because we can use your help.
Great.
Perfect. We had one question come in. Were any of your hindcasts validated?
Absolutely, yes. So most of our validations are being done offshore, because that's where we have more observations. So I showed one slide for the Pamlico Sound, right? So there's a suite of observations from NASA, NOAA, and also local agency and research team. So we put our hands-on observations for the validations for the hindcast. The same thing can be said for the St. John's River. So there's L1, L2, right? So we have done similar amount of validations for L1, L2. L3 validations were based on relatively limited observations measured by a number of point stations. So there's a sea level. I showed that one example. There's also a local salinity time series measured by USGS and NOAA. Again, if you have other additional local observations, let us know. We can use more local high resolution observations, especially for L3 model validations.
And for the folks in North Carolina, SECOORA, the SECOORA side of the house, recently has ingested all of Hans Pearl's Modmon station data. So it's now available. So at that L3 level, I don't know if you've gotten to the point of validating with that data yet, or have you?
Yeah, that's the next step. Yeah, so we're going to use Hans data to validate the L3 model.
And then we also have a few data points from the Albemarle Sound that we recently received from DEQ, Department of Environmental Quality, the water quality, oh gosh, I think it was water quality or is it fisheries, one of them. They shared data with us also, literally just within the last month or so. So we are starting to get some additional data points in that state agencies are taking, that are observations that are being made by like state agencies and other academic institutions. So we are happy to get quality controlled data from any of those groups. And the other side is we can ingest it into the SECOORA data management structure. And then the data is actually more useful for other groups as well, not just Ruoying and his water modeling projects, but it's also available then for other state agencies or other academic partners that could use that data for their research interests too. So we are happy to work with you on data sharing. That was my data sharing plug.
Great, Jen. And it looks like Melinda Simmons, she has 8 site time series where they collect a variety of water quality data just north of Site A in the St. Johns River. They have been sampling monthly for almost 4 years. Oh. And so I'll put you all in touch. She gave us her email address.
Thank you, Melinda.
Yeah, that's wonderful. Thank you.
Yeah, this is great. So yeah, so as Ruoying just pointed out, we do have the ability to do 3D along track. And in this case that you're seeing on your screen is salinity. And so this is based on water depth in meters. And as you see across the bottom axis, you see we start at point A and go through point E. So that corresponds with A on the map. And then working your way, I get confused on the St. Johns River. I guess that's up the channel, or is it down the channel? It's away from the ocean. But you're working from A through to E, sort of along the main stem of the navigational channel. And then the salinity level corresponds on the right-hand side from high of approximately 35 in the dark red to a low of about 10 in the dark blue. And when we hit play, such as we were doing with when Ruoying was speaking, you can kind of see the water pulsing back and forth, kind of moving from the salinity levels getting a little higher, moving from point A to point C. And then all of a sudden we start seeing a lot darker slugs of water coming in, and I think that was around October 8th. So our pop quiz for everybody is what was happening around October 8 to October 10 offshore of Florida. Do we have anybody want to jump in? All right, well, it was that little known storm, Hurricane Matthew. So so we are catching, we did catch that higher salinity water that moved in and then kind of quickly moved back off once those winds turned and we saw sort of that shift occur. So I'm going to hit pause. If we scroll down though, you're going to basically see, just like we did in Albemarle Pamlico, you can go from station A all the way down to station E, and you can get the predicted salinity level across the time period, October 3 to October 14. And we can kind of see as far back as, I guess it's just south of the Orange Park area, we're looking at salinity that's predicted to be roughly in the 18 parts per thousand range, that far away from the mouth of the river. And as you can see out here, we get to the mouth of the river. So again, you can use the map to investigate local areas. You can really zoom in to other locations. You can change, again, your salinity levels and see how far upstream you're having some amount of salt water move up into the river.
And we had another question come in. In the simulations you're showing, how is the hydrology addressed/determined? For example, freshwater flows into the river.
Yeah, in this case, we are using the national water models. So the reason, so when Jen talked about the transition, so initially you have a salt intrusion. So that's because when the Hurricane Matthew get closer to the Florida East Coast, so that introduces a strong downwelling at the early phase. So that allows the salty water being pushed in. Okay, but then the storm also introduced lots of precipitation and runoff. So that's why the national water model, this World Hydro model, is able to respond to that strong precipitation. So that's why you start to see several hours or days later, you have a larger freshwater runoff from the water hydrology model, World Hydro models. And that fresher water, larger river runoff go into the system. That's why you are seeing the freshening of this river channel in response to the precipitations and larger river runoff. So the whole thing is very dynamic. And when you link this high resolution river ocean model with the national water river hydrology models, you are able to start to see the interplays and also the evolutions of the salinity in this case.
Okay, and I think my other comment I was going to make before we really try to get folks to give us some more feedback is that, as I said earlier, we really are using salinity as sort of our base, I guess, layer of data for this product output. And this is really just to, like we said earlier, it's a wireframe, is to get people talking. So what we could do is have, if folks will tell us how you would like to see salinity and temperature, would you like to set thresholds where, hey, when salinity reaches, 15 and temperature is above 70, we need some kind of alert. Or, how do you want to select your predefined locations? You know, what are the better ways to kind of view the data together? I mean, so we really are using this as a starting point, but we don't want you to think salinity is the only thing we're working with, because it's not. We can use any output, any of the data that the model output provides, we can incorporate into the products.
And along the same line, so we've been talking internally within our team. There's a suite of proxy product we can derive. So once you have temperature, salinity, you can derive stratification, which has a very close relationship with hypoxia. For instance, the oxygen level in the water column. Stratifications can also be used as indications for turbidity. So this hydrodynamic river ocean hydrodynamic model can be used to derive a suite of proxy parameters that can be used to support water qualities and ecosystem management.
Jen, I'm going to jump in real quick and say,
yes,
you rattled through the points I was going to try to emphasize, but I'm going to give it one more go, and that is to say that the points you see here on the map are not set in stone, and we've dreamed about perhaps having you log in, or a user log into the system and define your favorite points of interest, and perhaps that user sets up like an automatic email that goes out to their inbox every morning for these points they've identified. So nothing here is set in stone at all. It's just we chose these points for demonstration purposes, and that's it.
I'm going to start with the base question. You know, is the interactive map with the different thresholds that you can change useful?
We had one feedback. Jerry said use defined ranges and points best. He agrees. Okay.
And I think what we may want to do, if folks are willing, is maybe Charlton and I come up with a few questions like, you know, is salinity levels like predefined ranges 36, 15, and 5 sufficient, or should it be 36, 25, 15, and 5? You know, kind of maybe get folks to give us some feedback that way if folks are a little shy on talking today. If you don't mind us emailing you afterwards, we'll maybe have a few pointed questions. Charlton, I'm going to go back to early draft visualization. This was very early. Charlton came up with this one. He took 2 different locations, and we looked at salinity across sort of a range of days. And then down here we had temperature. But, you know, we could easily switch this up, I think, where we have temperature and salinity plotted together, say, for the red point, and then another graph would be temperature and salinity for the green. And you can see we had magnitude, current magnitude here. So this was sort of one of our initial plots. But, you know, take a look at this one, too, and see if you see anything there that might be, you know, worthwhile. Charlton, do you want to comment on this one?
You know, those were humble beginnings. So I think Jen's right. We're trying to just throw everything out there and see what sticks. And, you know, we want to develop something that's really useful. So these are kind of the tools in our toolbox right now, but we have ideas of our own. It's just much more helpful if the users can really guide that discussion.
So Jen, I'm not seeing anyone disagreeing with maybe like a short survey after the webinar. So maybe we could send the recorded link along with all of these great links, web links that you all put together, and a quick survey to all the folks who registered.
Okay, that works for me. Ruoying, it's 12:52 and there was a question about Cnaps. Do you want to take back over and you can show the Cnaps model and how that's being used?
Well, I'm going to take over for a second.
Okay.
We had another question come in. What about chlorophyll and residence time?
Yeah, so chlorophyll is not something we are able to predict using these hydrodynamic models. But as part of this committee project, we are going to use the model to study the residence time. So which is actually one of the key scientific goal. So using the resulting models, we can look into better define, for instance, the spatial distributions of residence time in the Pamlico Sound and in the St. Johns River. So that's something we can definitely derive as part of this project. Chlorophyll and other ecosystem components, we're hoping to be able to be built upon. So once a hydrodynamic model is in place, we can add the ecosystem modeling components into that. But that's beyond the scope of this committee project. But certainly within our scientific interests, and we'd like to pursue in the future, probably as a different another project.
Perfect. And one more question. What kind of bathymetry data do you have for the St. Johns River?
We have 5 or 6 different sources. I don't remember them on top of my head, but there's a NOAA database, there's a USGS database. I think there are 2 USGS databases. I think there's also 1 local database. I don't remember, but I can come up with a list and communicate with the user to to go as many as observations as possible. So if you could send me an email, we can follow up, and love to learn more from you on what other data sources we can utilize.
Yep, and I will be sure to connect you guys over email. And I'm going to go ahead and promote you to presenter, Dr. He, so you can talk a little bit about Cnaps. And if anybody has any more questions, please go ahead and type them in, and we'll make sure that they get answered.
Okay. So Cnap. So is there particular questions about Cnap?
They just wanted a brief overview. So
Okay.
I don't know if you have like a 5-minute lightning talk on it.
Yeah, so Cnap, let me change this. So I went this very quickly. So Cnap is it's a fully coupled system, and I think if you go to, I think one good easy things to do is to go to this website. So go.ncsu.edu.cnaps. So that will take you to this website, and because this is a fully coupled atmosphere, ocean, and wave modeling system, so you can go to different tabs. For instance, if you want to check on the marine weather condition, you can go to marine weather. If you want to look into the wave, go to the next tab. And if you want to look into 3-dimensional ocean for the region, then go to the next tab here. So this not only showing you surface conditions. So in this case, just for example, we're looking at the current speed at 5 meters below the surface. So that's why the color shading here shows a very strong velocity along the Gulf Stream, right? So we are having more than 1 meter per second speed associated with loop current and Gulf Stream. So you can also check on temperature, salinity at different levels. So this is a 3-dimensional model. So from surface all the way to the bottom. Okay, so there's a suite of variables you can use to visualize the Cnap solutions. And there's also a function called virtual oceanography. So this is something, if you want to release some virtual particles, you can see how the particles is able to travel along with the circulation. If you want to look at the transect, you can use your mouse to select 2 endpoints, and the web is able to bring up the subsurface temperature or salinity along the transect. So there's a suite of user-defined applications you can do here. And on day-by-day basis, we were running the Cnap to provide them nowcast and 3-day forecast for this entire Northwest Atlantic Ocean region. And I just want to use this opportunity to say thank you to NOAA and IUS and SECOORA, because without their support, we won't be able to get the system up running and running on the day-by-day basis. So this is still very much a research product, and we do have downtime from time to time. We're not the operational agency, so we're a research lab, and but we are trying to maintain such a pseudo operations as much as we can. So, people are interested in utilizing the weather, wave, and ocean conditions. I think this is a good place. This website is a good place to start. And this also links back to our research website. There's a suite of publications talking about different components of Cnap. So if you are interested, let me know, and I can send you the journal publications if you like.
Great, thanks so much. We have 2 minutes left for questions. And as I said before, you guys are welcome to unmute yourself, or you can type them in the chat box. And we will be sure to follow up via email, and this webinar is being recorded, so we'll send you the recording link to that and a short survey.
So one thing to point out too, and within this project, I know Ruoying, I think, hit on it, but I don't know if we stressed it quite enough. He is developing this model in very close cooperation with folks at NOAA, and the goal is that these the model would transition to NOAA to become operational. So they've already started doing some testing on their servers for running the model, and that means any products we develop for you all could also still be maintained and used. So, this is not, while we do have a short-term project, this doesn't just all end at the end of the project. So we do want to let you all know that we are trying to do this for the long term, and that's why we really value your input, so that we can make sure that we're doing things that meet your needs.
Great, thanks so much, Jen. All right, I'm not seeing any emails come in. If you all have asked a question and we didn't get to it, I've already sent out emails to Dr. He and the team. And Melinda, we will connect with you about your water quality sampling, and be sure to follow up via email and URL. All the presenters are getting great kudos, so kudos to you all for the great presentation.
Well, thank you all.